To continue chapter 16, which is on renewable energy, most energy efficient methods to heat space, in other words, heat your home, heat the school. First thing is super insulate. Keep that cold air out in the wintertime and in the summertime. It's very cheap to insulate overall, and it is such a huge cost. That's a huge push in the United States right now, and it has been in other countries for a long time. Geothermal heat, which we'll talk about in a bit, that's using the natural heat from the earth in order to heat your home. Passive solar heating, open up a shade, let the sun in. Talk about that soon too. Conventional heat pump and high efficiency gas furnace. Notice the note here of high efficiency. Nowadays, our furnaces are about 95% efficient, much, much less waste than it was even 10 years ago. 6 types of renewable energy we're going to go through: solar, both passive and active; flowing water, which is hydropower; wind, biomass; geothermal; and hydrogen. It's well known that Europe has been ahead of us in this race to use renewable energy for years. A lot of it comes down to political differences in the United States. European Union, about 22% of the electricity does come from renewable energy. That was mandated by 2010. California, of course, about 12% of their electricity is from renewable. Kansas, North, and South Dakota rely heavily on wind. They definitely have the geography for this. North and South Dakota very flat, so they can really crank the wind out there. Nevada and California very ridden with solar. We can have solar power around here, but obviously much more efficient out there. If we just inundated North and South Dakota with windmills, or Nevada with solar power, we could actually create enough electricity for the entire United States. We would not need to burn coal and add pollutants to our environment, or oil for that matter. This is a little just design using passive energy, and just kind of think about this. If you design a house someday, a lot of houses even now, newer ones, will use a cool air exchange where we have cool air vents that go through an area kind of like a little solarium, which is where you can grow plants and sit in the sun and things like that. It has insulated windows, so it allows the heat in but not back out. Cool air, which sinks, will actually be displaced by the warm air, so the warm air will push it and we get circulation like this. It works a very, very good system. Note all the insulation in this home too. Another example of passive design that really comes into play even in the Milwaukee area. This has been done for years. If you go into Milwaukee a little bit, the bungalow houses typically have awnings on them, whether it be big ones that hang off part of the roof or above windows. In the summer, we take advantage of the fact that the sun is very high in the horizon. So what we do is build awnings that block that sun. In the summer, we don't want that sun in our house. We want to keep it naturally cool. Where in the winter, we have it in the lower horizon, and of course, it comes directly in and heats our home for free. That's passive. So we can orientate our buildings and greenhouses toward the sun. That's passive. Take a look at this excellent design. My guess is if this is in the northern hemisphere, this is facing south. You can see the awning to block the sun in the summertime, but as it's lower, it comes right in here and very easily heats that home. Also, ideas with this: you can use walls and floors that are made of concrete, adobe, and brick. What happens with those is those are excellent at absorbing heat during the day, and then at night when you need more heat, it slowly releases it. You can get 30 to 40% lower heating costs with that just by design. This is an example of active solar energy. Active because it does take some energy to do this. What happens is this person has run coils on the roof, generally a dark color, to absorb the sun's energy. They'll pump something like water or an antifreeze product through there and actually capture the sun's energy. They may store it in here. Maybe if it's water, they'll use it for a shower down the road, or what they can use it as a heat exchanger, and it can be sent throughout the house and actually heat up your home. This is just kind of an example. These probably have a liquid in them, these solar panels right here, and it captures the energy, brings it to a water pump. It is active. It absorbs the sun's energy by heat absorbing fluids stored in gravel, water, clay, or chemicals for later use. So what that means is, like in here, there might be gravel in there, and of course that'll hold the heat and re-release it later, so it doesn't lose the heat as well or as quickly. Just another example. This is actually something called earth tubes. They use these out west quite a bit. If you go down, like in California, they use them. If you dig down into the earth, it's quite a bit cooler there. So what they can do is in the winter or summertime, when it's really, really hot in your house, they can actually pump warm air out of the house, I'm sorry, they can pump warm air out this way, and they can bring cool air in through here, and it actually cools down your house. And all you have to do is basically put a fan right here to suck that cool air up in there. It's a very, very easy design, and you can see this is just another example of passive where in the summer it's up hot, or up high rather, creating hot air. Up here it's blocked from coming in the wintertime it's lower. Great design. To cool houses, we can use those earth tubes, definitely super insulate. Open the windows for a breeze instead of turning on the air conditioning. Create a cross breeze where you have windows opposite each other or doors opposite of each other, and it'll create a nice cross breeze in your house. Using ceiling fans does wonders too, and it's actually pretty efficient. Block the sunlight with trees, particularly, which works really well in the summertime. Deciduous trees. Deciduous will block the sunlight from coming in, and then in the wintertime when the leaves are off, the sun will readily come in because the tree is not blocking it. Window overhangs, light colored roof or siding, what that does is reflect the energy right back up. Solar thermal systems, a couple other uses. This is something called the central receiver system right up in here. This is out in the Mojave Desert in California. These are all mirrors, and what those mirrors do is focus the sun's energy, and they actually track the sun. They focus it up into here where there's a oil product up in there. And what that does is it heats up really, really, really hot, as you can imagine, and it creates steam that can actually turn turbines. So this is it's very expensive to set up, but once set up, it's awesome. Solar cookers, of course, a lot of nations rely on solar cookers to cook their food. This is a huge solar cooker right here, directing the sun's rays with this concave design right into this right here. And of course, what that does is eliminate the need for biomass. Solar cells, these are also active, are actually photovoltaic cells, also known as PV cells. These convert solar energy into electrical energy, generally into DC, and then that will be converted to AC for your house via inverter. These are PV valves right here. You can put them on a rooftop. You see these around the Brookfield area occasionally. They can actually now put these in paint. So you can paint the side of your house like black or a dark blue color and actually get electricity from that. Generally made of silicon. India, Zimbabwe are definitely using these quite a bit more. We're looking at getting organic cells, which are made of paper. They can be placed literally anywhere. You see these all the time along the highway systems. In Brookfield, they have them. That way they don't have to have battery packs that need to be recharged constantly. They don't need to hook electricity up to them. There's actually backpacks that have cells like this that actually you can plug your phone into. So when you're on the move, you can, as long as the sun is out, you can get energy from it. The reality with solar, it's free, it's reliable, it's quiet, very minimal maintenance once running. It is cost competitive long term. Little lower net yield because of the high cost initially and the land use in order to get like silicon. It's modular, so you can be put apart. You can add more to it. Very high net energy overall once rolling. Well-developed technology, and there's no CO2 emissions from this. Hydropower. This is an example of hydropower. This is the Hoover Dam. Water behind a dam turns turbines. So what happens is you can't really see it, but in here water is taken in, and there's turbines underneath here, and the water rushes out over there. What happens as it turns it, of course, it is converted into electrical current. Really three methods to do this. There's a large dam, which is a dam across the river, creates a reservoir. The other great example of this is the Three Gorges Dam over in China, which is on the Yangtze River rather. Small scale, low dam, little reserve. We do have some of those left. It's kind of a dam across a small river or a stream where they don't really make a big reserve like this behind it. It just uses the natural flow of a river system generally. There's pump storage. Pump storage is not great. It's got a low NPP. Uses surplus electricity from a lower reserve to a higher reserve. So that would be like pumping this water back into this area up here and then rushing it through again. Again, lower NPP, not a great design. 20% of the world's electricity is coming from hydropower in 2002. That's quite a few years ago, so that's obviously increased from now. 99% of Norway's energy comes from hydropower, 75% of New Zealand's. Excellent, excellent. Current funding of large-scale dams is decreasing in the United States. A lot of that is because we're ruining habitat for things like fish, migratory patterns of birds. There's the idea of now of tidal and waves that are used. The problem is it's expensive. You can see this design right here out in the ocean, for example. As the tides come in, it actually rotates these. So again, free initial cost is quite expensive though. Hydroelectric, not cheap to build. That's the big knock on hydroelectric power, is it tends to be very, very expensive initially, but then the operating costs are quite low. It does control flooding downstream. Above stream, you can use the area for recreation. In other words, you can use it to for water sports, for skiing, for tubing, for water skiing, a lot of other things. You can use it for irrigation. It does have a high net energy yield afterwards. Wind power is the next one. It's the most rapidly growing method. You see that in Wisconsin. There's hundreds of these just north of Milwaukee now. It's increased 7 times from 95 to 2004, and that's going up even further. 3/4 of the wind power still is in Europe, though. It's on and offshore. They actually put these things out in the oceans now. Denmark has abandoned coal burning, good for them, and they've gone almost solely to wind power. Oklahoma, South Dakota, North Dakota, Kansas, we're in there now too. If we throw Nebraska, Texas in there, it's deemed the Saudi Arabia of wind. In other words, we don't need to rely on outside sources of oil anymore. We have our own here. More, if we just inundate those states with them, we'll produce tons of electricity. More advantages than disadvantages. The big disadvantage at the beginning is, of course, cost. The cost overall is the same as coal, natural gas, and hydropower by the time you think about mining or drilling for these products. Here's just a typical design. If you've seen these north of Milwaukee, they are absolutely huge. The cool thing is you can still farm below it, and those farmers make money just by generally production off of these things. Another little shot of them. High net energy, low electrical costs, low environmental impact on these things. They do have to install these around here in the wintertime because the ground is frozen, and the big trucks that go in, the big semis, are weighted down by these huge windmills. So when the ground's frozen, it's much, much easier. Plus, I know they need to install, I think it's an 8-foot deep concrete base in order to hold their massive weight. So very quick construction overall. They come pre-assembled and just put together on location. They can be located at sea. They can be located out in the Great Lakes. That's a huge idea right now too. Land below can be used for farming. The problem is they need steady winds. You do need a backup system if you don't have winds. It can be visual pollution. Noise associated with this can be an issue too. The big knock on it is migratory. Birds can actually get caught up in these more so. I know in the ones north of Milwaukee, bats will get in them when they're not moving. They'll nest, and then of course once they start moving, it's not a pleasant situation for them. In this area, we have something called a Niagara escarpment. This is all the energy resources that we use. If you look, we have coal burning plants. There's a huge one down in Pleasant Prairie area. There's one in Oak Creek. I'm not sure where this one would be here. Oh, that's in New Berlin, I believe. Madison has a coal burning plant right near campus. Up in the Portage area, up near Wausau, Green Bay has a couple coal burning plants. A couple other things on here too that it shows natural gas. Natural gas, of course, is a much cleaner burning than coal. Those are popping up all over the place. A huge new one up in Green Bay, as a matter of fact. So, but what we're doing with wind power is there's this thing called the Niagara escarpment, which is actually a higher level of land that goes all the way from here, all the way up through Green Bay, up into here, all the way over here, over to the Niagara Falls region. The idea of that is it's slightly higher than the rest of the ground. It's kind of like a little hill, if you will. That's what an escarpment is. Put them up there, and then they can catch the energy from the wind much better. Biomass, another idea, great idea. Plant and animal materials can be burned. A little iffy on if we're reducing CO2 on this one because we're burning plants. Think about a farmer that is harvesting corn. A lot of times the waste afterwards is just, it could be returned as nutrients to the soil, but a lot of times it doesn't have a lot of nutrients on it. We can burn that stuff. 90% of energy in the poorest countries actually comes from biomass. You can see the people on the bottom actually getting probably manure, and what that manure has a lot of hay and straw and grasses in it, yet they can actually dry that and burn it later. So we can use crop residues, we can use animal manure. Biomass plantations are very, very fast-growing trees that are growing, of course. They're chopped down, they're let naturally dry, and then we burn them. Crop residue can be used, as I said, sugarcane, rice, cotton, animal manure, gathered, dried, burned. Some of the biomass can be converted to gas and liquid biofuels by bacteria too. It's called biogas. Biogas is generally a mixture of 60% methane and about 40% CO2. So we are still putting out some CO2, which is a global warming agent. It can be used for heat on farms though. So what we're doing with this, if we have, for example, cow poop, we can actually take that cow poop as it naturally decomposes, it produces this methane and a little carbon dioxide. We can burn that methane, and farms can actually use it for heat or for energy in a lot of farm procedures that they do. Landfills, of course, think of the Shire. We could drill into that, and new landfills, new sanitary landfills, they have to do this. Naturally decaying garbage can be used, the methane can be used to produce electricity. We'll talk about that down the road a little bit. China has 500,000 biogas digesters, so they're actually doing a great job with this. A little hesitant on the biomass because that still can release pollutants, but it is a renewable energy source. Ethanol is something that's huge in Wisconsin. Made from sugar or grain crops, we actually use corn in the great state of Wisconsin to make ethanol. As you know, when you go to the gas station, gas has ethanol added to it. And what that does is it makes a cleaner burning product. It burns really, really hot, so not all vehicles can use it. It does have a net energy loss, of course, and the problem is corn prices are going up because of this. The other side of corn is we grow corn in order to feed cattle, and corn prices are going up, so therefore beef prices are going up. Gasoline, of course, and ethanol mixtures for gas engines. We can also get methanol, which is made from natural gas. So natural gas is mainly made up of methane. We can get methanol from this, which is liquefied, but it does have CO2 in it, and but it can be burned, and it can be used to replace gas if needed. Producing ethanol, a little case study. We can use crops such as sugarcane, corn, switchgrass. Switchgrass is a very, very fast-growing grass. Agricultural, forestry, municipal waste can be all converted to ethanol. It's a very, very clean burning product. Switchgrass, of course, can remove CO2 from the troposphere and store it in the soil. So another good thing about switchgrass, not only can we burn it to use make electricity, but it'll actually take some of the CO2 out of the atmosphere, which is awesome. 10 to 23% pure ethanol makes gasohol, which is the stuff that we use around here. Some vehicles are known as E85 or flex fuel vehicles, and there are gas stations that carry that around here. It's 85% ethanol. It's got to be burned in a flex fuel car. If you put that in a normal car, it'll actually melt your engine because it burns so hot. Processing all the corn grown in the United States into ethanol would cover only about 55 days of current driving, so it's just not really worth it, unfortunately. Biodiesel is made by combining alcohol with vegetable oil. That's another huge design. Some people are actually converting, buy a kit for like $1,500 to convert your car over to biodiesel, and you can actually go to McDonald's and get their oil generally for free that they use in their fryers, and you can actually use that to run your car, which is awesome. Apparently your car kind of smells like French fries though. Biodiesel has the potential to supply about 10% of the country's diesel fuels. They are using it in things like buses and mass transportation in a lot of areas. Next one is geothermal. This is awesome. Geothermal uses heat pumps to bring underground heat up. As you can see right here, a lot of new homes, Fond du Lac High School is actually heated solely with geothermal. What happens is we have an exchanger and it pumps heat in these pipes that are located underneath, probably like 10 feet down into the ground. And what happens is we use the heat from that, it's pumped back into your house and it's circulated throughout your house. Expensive to set up, but once set up, this is awesome. It's used as a heat source in winter, heat sink in the summer. So when your house gets really hot in the summertime, the heat actually goes into here and we put that heat back into the ground. It's kind of like the idea of living in your basement. You could probably live in your basement year round without any heat. Same idea. Your basement, our basements around here stay anywhere from 58 degrees to about 65 degrees, which is very livable. The only problem with this is in our severe winters, of course, sometimes we need a secondary furnace just to back it up. Um, Most energy efficient by far. It's cost effective. It's environmentally friendly. Big buildings are starting to tap into this too, as I mentioned, with high schools being used. 85% of Iceland uses this. Now, Iceland is very unique in this manner because they have a lot of volcanic activity that's active, and they can actually tap into really, really warm sources for this and produce steam and produce electricity with it. We're not there yet. It is expensive. It can be depleted in local areas. We're great with this here. Can't use this like in Arizona because it's very hard to tap into the ground in general. There are reservoirs in other nations where they have dry steam very, very deep down. They can get water vapor off these things. Wet steam where they have water vapor. They can get water droplets from this, again, generally from volcanic activity underneath the ground. And some use it to make hot water. It's tapped in rocks. And of course, if they're hot enough, like I said, in Iceland, they can actually bring this up and use steam to produce electricity with turbines. Works great. It is a depletable resource. Only certain areas have molten rock or magma. We don't in the United States, unfortunately. Very limited here with that. Hydrogen is the last one. Hydrogen is actually a very, very promising energy source. It's produced from water and organic molecules. It's very non-polluting. Water vapor, when burned, it says that it should be ready by 2020, 2013, and that is for consumers. It's currently available. A lot of European nations are relying on this. Out in California, they're using this quite a bit too. It might be possible to use bacteria to create this. The problem with it, so basically what we're doing is we're taking water and splitting it. And hydrogen, as you know, is a very explosive. That's what the Hindenburg was made out of, or used to float. The problem is it's chemically locked up in water and organic compounds. So what happens is we need to take a little energy to make a lot of energy. So the NPP does come down. Fuel cells are very expensive with this, but they are designing those and making them better. It's hard to store this too. That's a danger which was talked about before. If we use this in cars, it's great, but what if a car gets in an accident? How will hydrogen affect the atmosphere too if we release that? Storage options, we can compress it, we can liquefy it, we can store it in a metal hydride compound, or we can absorb hydrogen with activated charcoal. We can store it in a network of water molecules. Basically what this slide is showing is we're having issues with storing this stuff right now because it's so volatile. A couple of things that really come into play with this too is net energy. Primary energy sources. The sunlight, of course, the sunlight indirectly makes wind. It indirectly makes biomass because plants need the sun in order to grow. Fossil fuels indirectly come from this. We need to make electricity, and we really need to convert a lot of these things over. With hydrogen production, we need to set it through a process called electrolysis, which is separating hydrogen from oxygen. That takes energy. By the time we transport it, we could do it in big trucks, in vehicles. By the time we store it, and by the time we actually use it, is it really worth it? So we need to look at life cost of this stuff and overall efficiency. Priorities, we need to decrease greenhouse gases. If we didn't have the issue with greenhouse gases and pollutants, we could burn all the coal we wanted, but that is a problem. We need to reduce our dependence on fossil fuels. We need to improve fuel efficiency. With cars, we're getting there. Right now, if you buy energy efficiency appliances, or if your parents do, they actually get tax breaks from that. So they get money back from the government at tax time. People buying hybrid cars actually can use it as a write-off, I believe, once on their taxes. Public transportation with less polluting natural gas, big buses, for example. Think about the buses going down to Summerfest. If we would just move more people with less pollutants, it would be so much better in our environment. And obviously, increasing research on this is incredible or important. Another thing we need to do is something called decentralized power. Now, we have all these great potential power systems like small wind turbines, bioenergy power plants, wind farms up here, solar power. But the problem is we need to get it to our homes. And unfortunately, what happens is by the time we produce the electricity, let's take the wind farm up here, and then we need to send that electricity over energy lines into your house. Now what happens is when we send it through power lines, we get resistance. So what happens is we have 100% energy here. By the time it gets to you, it might be down to 20% energy. So we need to cut that net energy loss. We need to decentralize micro power systems. Another picture down here, we have a power plant right here. By the time we get that to our like a communication headquarters and then to your house, we've reduced efficiency. A great example around here is our energy comes from down in Oak Creek. 100% energy down in Oak Creek, but by the time it goes through all the transmission lines, by the time it gets to Brookfield, that net energy decreases significantly, and it's a coal burning plant, so our net energy really decreases. The best thing to do would be for Brookfield to have its own power source. Let's throw some windmills out by the Shire or north of Capitol Ave or something like that. And what that would do is by the time it gets to your house, the net energy would be much higher than trucking it in or pushing it through all the way from Oak Creek. So that is getting rid of a decentralized. Decentralized is its Oak Creek provides all of it for the Milwaukee area. What we should do is have a power system in Brookfield, a power system in Waukesha, a power system in Wauwatosa, Mequon, and so on. So they all drive from that, and net energy is so much higher. The best thing to do is at school have solar panels on here. That would be direct into our school. Put some windmills on top of your house or something like that. Obviously, there's problems that come into play with that idea. Money, another huge problem with all this is money spent by the United States from 1948 to 2003. Nuclear energy was a huge 73 billion, as we know, done. We're not spending it much more into that research at all. Fossil fuels about 32 billion, renewable energy a mere 19 billion, and energy efficiency only 15 billion. If we were just to put more money in renewable energy resources and energy efficiency, particular conservation, and not wasting this energy, we would have so many problems solved. That is it for chapter 18.